We are starting our session. So, as I have been already that shared with you that what will be the today's topic will be there. So we are going for the today's topic. Wait. We have been completed these. Okay. So that is the. Wait for a minute. Now that's fine. Screen is visible to all?
Yes, sir.
Yes, sir.
Right. So today we are going for the topic that is solving relational and first order logical Markov decision process will be there. In that topic, we are going for the things that will first will be that we are going for that introduction will be there. In introduction, what will be there? We are having that representations and techniques for, we have already that go through that Markov decision process. MDP, we have already studied the MDP, we have already studied. And now we are concerning this MDP along with dynamic programming and what will be the objects and their relations, that how we are working on this MDP, and in that concern we will just go through it. So such that we are having that the relational world in that we are living. So everywhere in planning domains will be there, just like the games, real world, indoor scenes, and many more things will be there. So the relational representations, what the relational representations allow, it allows us that expressive natural data structures, and that captures the objects and their relations in an explicit way, and generalize our objects and their relations with similar problems and different in the number. What that means? That means in that reinforcement learning, what happened? We are having that different objects will be there, and whatever these objects will be there, in that reinforcement learning, we make some relation among these objects, and what with the help of this relation, what we are doing, we are estimating that what will be the next step for that next action that will be going on there. So that is now we are taking an example will be there. In that example, we are having that wait. Okay. As a human, we can speak we can speak, we can think, and we know that thing that this world, whatever in that world we are relying, we are having that objects there, and in among these objects that we are having some relations are there. With the help of that relation, we are just analyzing the things with them. So that will be there, right? So the objects maybe we have put down, taken an example. The objects will be, the tables will be there, houses will be there, tables inside house will be there, books on the table, and so on we are having. So we are equipped with that inductive bias will be there, where we are having the producers and divide the world into objects. Basically all these objects will be there, and what will be, we are doing the main, we are doing the interaction of these objects. What will be the interaction of these objects? And we are applying, basically we are applying what? We are applying an computational module that represents these objects with an meaningful sense. If I am saying that this is a room, and in that room that we are having table, chair, that doesn't mean anything. But when we are relating that thing, this table and this room is used for conducting in class. So what we are doing, we are just relating these objects with some that activity. So this computational module will be for that is then important thing. Now for that intelligent agents, now we are discussing that in reinforcement learning we are having that intelligent agents will be there. Here what happened? Agent, intelligent agent, you know, no? That will be that we are using that, what will be the agent that will be working behalf of that we are having that some this will be there, no? we are having some cross problem will be there, and we want to go, this is our target and we want to go to there. So what will be the possible ways will be there. So this is the intelligent agent who can work behalf of us. Okay. So purely these agents will be there, and this agent will be working with their that the objects, and what will be their properties and their relations with their objects. So that will be going on there. So furthermore, such representations are highly effective, compact the description of world in terms of objects, simple interactions that will be we are using. So now the last decade, we are having that reinforcement learning has merged and tried to do these intelligent agents are playing very crucial role in that our reinforcement learning that we are using for that knowledge representation, probabilistic or the first order logic that we are right now discussing. So that will be going on. So to deal with these objects and relation, we have required some reinforcement learning algorithms where we are taking some decision theoretic learnings and complex uncertain world, we can go ahead with them. So this field, relational reinforcement learning, takes an inspiration representational methodologies and algorithms from the diverse fields such as reinforcement learning, logic based AI, knowledge representation, planning, probabilistic logic, machine learning, and cognitive architectures are there. So in many of these areas, we are using that objects are there and the relations are there, and the assumptions of that reinforcement learning will be there, and we are applying these assumptions on that in this field, just like we are having the conjugative agents will be there and their behavior and how they investigate their which algorithm, reinforcement algorithm will we interact with these objects, and how do we get that first order logic, and all these things will be going on there. So relational reinforcement learning offers a new representation paradigm for reinforcement learning that tackle many problems more compactly, efficiently, and that is the state art of proportional approaches that it will be uses. Here we are using also, we are having that new opportunities will be there where we are having if we are having additional background knowledge into algorithm, surpassing, tabula rasa learning, so these will be there. What that means from that, what will be the core of these things will be there. What will be that in reinforcement learning, if we are having that background of that something work, we can deploy that thing, and we can deploy that reinforcement learning when we don't know what will be that environment and how will be there. We have already taken that our curiosity rover example in that Mars, we have already discussed that thing. Okay. So now we, you know very well that this MDP will be represented with that star will be there now. What will be S will be that, what will be S? S will be the state, A will be the access, T will be the transaction, and R will be the reward will be there. So what is that here? We compute that some value functions will be there, and we are using these value functions V and Q will be there, and we are just computing a policy, and the policy will be represented by the pi. Okay, right. For this Palitoria algorithm exist, which all or less, more or less, fall the category generalized policy iteration. GPI is there. General policy iteration will be there, which denotes iterative looping involving will be there. First, we are evolution will be there, policy evolution will be there. After that, we are computing for the V and pi, and after that, what will be, we are going for the improvement, then computing, and then improved whatever that we are having the pi dash and V dash from that we are getting from this thing. So what here we will be there. So what we are discussing in that journal policy iteration, that what will be the looping will be going on. First, that we are discuss about, that is the policy evolution will be going on. After that, we are computing that the value of V and the pi will be going on. And after that, the policy improvement we will be seeing. And then computing, what we are computing the improved that pi dash. Pi dash will be here. That will be that new, what will be the next step will be there. And from where we are getting that what will be the existing policies V dash, what we have been policy evolution, and whatever the existing policies we have been go through it. So next, we are using that the policy iterations using abstraction and generalized techniques will be there. So we will represent this policy iteration using abstraction and generalization technique. We are nominated with the Pygate. In Pygate, basically you have been seeing that you are having Pygate 0, Pygate 1, Pygate that is 2 will be there, and Pygate 3 will be there, and we are having the abstract level and flat MDP will be there. So what will be going on there in Pygate 1? What will be the existing policy will be there? What will be that policy evolution, and this thing will be there. We are finding the value of that v pi will be there. If that is according to that, whatever the policy evolution, this thing will be there, that will be going on. But before this Pygate 0 we have been started, and then we are comparing with that Pygate 3 and their abstraction level and flap. Now in detail we will be studied that how this Pygate 0, 1, 2, 3, what will be their significance, how they are concerning with the abstraction level, and what will be the flat MDP will be going on there. So first thing that what is Pygate will be there. So we formulate a more general concept of Pygate, which makes the use of representation of here we are using that representation will be explicitly we are using. So we are having that 4 ways will be there. With the help of these 4 ways in GPI, we are representing these Pygates will be there. So what are these four ways will be the Pygate 0, Pygate 1, Pygate that is your Pygate 3 will be there. So what is the Pygate 0? Pygate 0 is the first generating a compact representation that was used in abstract level. Example through that model minimization or feature extraction we are using. After that, what happened? We are having the 2 Pygates will become, one is Pygate 1 and one is the Pygate 2 will be there. They are close to the GPI and they are assumed to be fixed representation and learn either they are learning with MDAP related functions, that is the value of Q and V function what we have been using over this abstraction over that Pygate 1, or they can learn that different parameters what we have been fixed. Example will be that we are using that the neural network representation will be there and we are using that simultaneously Pygate 2 will be there. What will be the Pygate 3 will be there? Pygate 3 it will be the methods that are most generally that they adopt abstraction level while solving for any MDP will be going on there. So you have been seen there. Here we are having the Pygate 0 will be there. Then Pygate 1 will be there. Pygate 2 will be there. Pygate 3 will be there. Their abstraction level will be there. Now we are concerned about that what the flat MDP will be going on. So in Pygate, since this relational reinforcement learning, all these representations will be upgraded from the RL. So we are looking for the abstractions. Why that? What are the distinguished 5 types that we are using in MDP? So we are using that first one will be the states that we are using. That is the state space abstraction. Second one is the factor MDP representation. Third one we are using that is the value function. Fourth one that we are using that is the policies will be there, and fifth one will be the hierarchical decomposition will be going on. So this Pygate what will be focusing will be there. So whatever the relational this reinforcement learning and whatever these MDPs we are using these objects and these will be there. So how that we are closely that tightly we are representing these things will be there. And the other words what we can say, only learn what can represent the basic motive will be there, what one can represent that will be there. Even though there are many various that we are having that various ways of representing that knowledge, including that what it includes includes the rules, neural networks, entity relationship models, first order logic, and so on. We are having that some of these representational classes are also exist, that is the atomic will be there, proportional will be there, decade will be there, and the relational will be there. So now, whatever these all these 5 classes, whatever these 4 classes we have been going on through, now we are going for that depth of this thing, what the atomic, proportional, and these will be going on. So the first one will be the atomic. The atomic means here that the description of algorithms and their proof and so called, we are having that descriptions of algorithms will be there, their proofs will be there. So we are saying that that will be known as atomic state representation, where what will be there, what will be the space S is there, and the space S is a discrete set consisting of discrete states will be there, just like S1 to Sn states will be there. A will be the set of actions will be there, and no abstraction generalization is used for all computation and storage. Example values happens according to the state wise. So this will be that your first one. And what will be going on in second one? In second one, we are having the proportionals will be there. This is the most common form of MDP representation. Each state consists of a vector attribute value pairs, where each attribute, just like that, their feature random value variables that represents in a measurable that quantity of a domain. Features can be binary. Features can be, we are using that binary or the real world values. Usually that we are having that set of actions. So here we are focusing on set of actions will be there. We are having that discrete sets. We are already having the discrete states will be there, but here we are having the discrete sets will be there. And we are using that example that decision trees will be there. In decision trees or soft that is support vector machines to represent value functions, their policies, their generalizing over the parts of state space will be going on. The third one that we are using, that is detect, will be there. So in detect representation, what happens, whatever the proportionals encoding will be there, they are used as an object. For example, the value of features, the color of an object is in my hand, could express something about a specific object without explicitly naming it. Okay, and distinct representation as well as object-oriented representation still proportional, but brigade the gap of explicit relational and formalism will be going on there. Next one will be the relational will be there. A relational representation is an expressive knowledge representation format in which objects and relations between objects can be expressed in an explicit way, will be discussed in the next section we are going on. So now that you are having little bit difficulty about atomic, proportional and what they are doing, but when we are doing the practical things, then you having the clarity what will be going on there. So this will be basically the representation will be there. What happened? We are using that reinforcement learning will be there. In reinforcement learning, atomic will be there. After that, proportional will be going on, and then first order will be going on. So here, what happened? The first order MDP we are using, and we are having that how that these things will be going on. If you are using with the ML, then what happened? Proportional machine learning, intuitive logic programming, and SLR we are using. If we are using in the planning phase, then what happened? We are using that classical planning action formalizing will be there. So whatever these representation that depend on the, we are having the different domains will be there. Just like psychology is a different domain, mathematics will be there, logic will be there, AI will be there. Here we are using that control theory, operation research, probability will be there. We are using agents, logic programming, and philosophy will be there. So what will be there? That is a block diagram of first order MDP and how that reinforcement learning, this one RL will be interacting with them, how that ML will be interacting them, and how this planning will be going ahead. See, all these will be there. And among these, whatever these three, what we are saying, that is pillars, or we can say that verticals will be there. Among these three these vectors or that pillars, we are having that different domains will be came. So now we are having that relational representation of a scene will be there. What now we will just wait for a moment. Now we will see that we are having a room is there. Room 1 is connected to room 2 is there. So here what we are using? We are using here will be there. After in room 2, what happened? We are having an object will be there, that is the table. And on table, what happened? We are having that mug will be there, and mug is having that property that is red color. That is okay. So now what happened in that room 2, either that what you are using, that is in, on, we are having that pot will be there, on will be there, next will be there, or this will be there. It may be that will be there. Mug 1 will be associated with mug 2 will be there, and mug 2 will be that color blue will be there. And this table, where this table will be existing, this table will be on the floor. So what kind of actions that we can going on these three? First, we can pick up that mug 1, then mug 2, then pick up pot, then go to room 1. So these are the actions that we can do on. So that is a relational representation of a scene in that reinforcement learning. Any doubt there how that we are representing these things?
Sir.
Now, what is that generalization of a probabilistic action? How that these probabilistic actions will be working there? Now we are just using this one. Here R and TR and M1 on T. What we are using, that whatever we have been done this one with the previous, we are having some actions will be there. Now pickup and this pickup 1, 2 and this thing will be there. Now we are representing in the mathematical formula the probability that what will be the probability of these actions will be there, that we are just considering on M and T what we have been taken. So if we are pickup, so we are having some value that is 0.9 will be there, and either we are carrying for M or we are not on, that M and T will be there. And 0.1 this one probability will be for that if we are not on to that M and T, and M and floor we are taken, and that will be broken will be there. So whatever we have been discussed on the basis of these actions, we are just going for the probabilistic actions. That what actions you can make your own example here. Okay. So now that is the relation representation and logic generalization will be there. So initial we are having that some states will be there. What will be that? This A, B, C, D, E. These will be the states will be there. And we are having the goal state will be E, B, C, A, and D. These are our goal state will be there. So what will be that initial state? Move A to D. What we are doing? We are doing that move A to D. Second will be move B to the floor. Third will be move C to A, and then move E to B. So that will be that if we are moving like that, so our goal will be achieved. We are on that goal state. So how that we are representing with the help of the root? We have that goal ON. Goal we have been just activated on that, which one? That is A and B, and we are having the number of block and C will be there. After that, what action we have been putting on, that will be on D and E, that will be going on. Here we are having AB now. AB will be there. C number of blocks will be there. And what actions we have been put it on? We have been actions put it down for the D and E, that will be going on. So now what happened? We are according to these logical generalization and this the representation. What we are doing on A and B, if that thing will be yes, okay, that will be going on in that this probabilistic this one. So the value will be 0.0. If that is not, then what we will take? Okay, we will clear that. That will be that clear A. And if that is S, we have put down some value. If we have that answer will be no, then we are going for another one. Then we clear that E, and our yes value will be there and no value will be there. That is you have been discuss these all three things in the while you have been just go through with data structure. In data structure also we are having that we are having some baskets will be there. In baskets we are having that moving the items for these grammaticals, and we are having so that all things we have been discussed. So above that, what will be that example will be there. What we are doing, we are having that our goal is A comma B will be there, and the number of blocks that we are having, that is the C will be there, and action will be D and E will be there. So same thing we have been representation with the help of that this diagram, and this diagram will be known as that is your relation representation and logical generalization will be there. Now, we are having that model based solutions techniques will be there. Here that models based these algorithms, they are having assumptions that a full abstract model that we are using. We are having that RMDP is available. This model will be available such that it can be used for dynamic programming DP algorithms to compute the value of functions, and their policies will be there. So the characteristics solution pattern of following series purely will be the deductive steps will be there. First, we are initializing that with that V will be 0, and we are taking with that whatever D value we have put on with that pi will be at 0. Then we have taken that 1D. According to that, whatever the decision we have been taken, that the value of V will be increasing, and precisely that value of pi will be going on. So same thing that will be going on up to which level they are going on. They are going for that kth level, and here also the pi will be going on for the kth level. And same thing if we are deploying that dot 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 will be there from up to what level we are doing for k plus 1, and here we are going ahead with k plus 1 for the pi. So on this whatever this RMDP will be available in that model based algorithm, we are using this mechanism. Now, whatever we are having that seen there, now their explanation will become the initial specification of problem will be viewed as a logical theory. The initial reward function will be represented was R. It was the initial zero step value function. We are having that V tilt value will be 0. Same thing will be there now. V tilt value will be 0. So that will be there. And next one, what will be there? Each subsequent abstractor that these functions will be going for that k next step, that is k plus 1, and obtained from that is v dash v tilt by, and the deductions what we are doing that will be representing by the d. So same thing whatever we have been discussed there. So all these working will be explained in that particular specific slide. So now we are discussing that whatever these all these what you can say the model based solution technique what will be going on there. Now we are discussing these model based this solution according to the Bellman's consideration, what the Bellman's is equation was doing with that thing. So here what happened in Bellman's equation, you know, we are starting with that v will be there, k plus 1, and s will be there. We are having that multiplication for this thing, and we are going for max whatever they have been belong, and the new states will be find out, but that will be depending on the value of vk what we have been put down. So these all these things will be representing in the structure of the that is the Bellman backups will be there, where the matching overlap will be there. So first we will look out that S dash state. S dash means that is the new state that is reachable by some action, and what will be that action will be there. This will be that the value what value we are using, that is vk, and S dash will be k, and we are using some regression will be there. So value is computed by backing up the value of state that can be reached by performing some specific action will be there, and equally that equivalently if you know that this value will be there, so we know that states will be there as, and transactions will be there, and what will be the new state will be there. We are comparing with 0, and then we will infer a partial that q value we have been find out. According to this q value, we are comparing with that q value with the state and actions what you have been that state and the action what you have been taken, and we are doing with the mu. And we are having that composition what will be, we are having the compositions will be there, and whatever the summation we have been using, that we have been representing this one, that already in that our diagram this will be there. And we are having that the maximization function will be there, that maximization function will be carried out by the k plus 1 size, and that will be applicable to the all of the actions. So that's all for today. Tomorrow we are going for hierarchical that approaches will be there. We are going ahead with the hierarchical approaches. Any doubt in today's lecture?
Sir.